aren't you recording? Now we're recording. Okay, so yes, the people at home can hear you if you're loud. Everybody say hi. Yeah, they can hear. Oh, that was good. We're starting a new unit, Unit 3. Unit 3 and Unit 4 are actually pretty quick units, very student-friendly in terms of grades. So I think y'all will do very nicely on this, mainly because it's very math-oriented. And anything with math, you guys seem to do well, as opposed to theory. Theory always seems to cause you guys problems. So it is a unit on gas laws. Who can remember, what are some things you remember from gas laws? Just random things. Eric? 22.4 liters in a mole, what does that mean? Every mole, right, a mole of any gas in the whole wide world, it has a volume of 22.4 liters if we're at STP, which is standard temperature and pressure, and we're going to review that. What else reminds you of gas laws from Chem 1? Alyssa? Oh, she's a nerd. Look at that. She threw out R is equal to 0.08. Naked perv, nerd, yeah. Nice. 101.325 kilopascals is the standard pressure in kPa. All right, good. So we know some things. That should make today very painless, I hope. So moving on to looking at some units of pressure. This is an old-timey way of measuring pressure. Who knows what the name of this piece of equipment is? A thingamajigger. Okay, no. A close. You put your emphasis on the wrong syllable. A barometer, okay? I have one hanging in the back of the room by the thermometer. It looks like a clock and then a little clock. The little clock is actually a barometer. That's another more recent version of a non-digital barometer. But basically, this type of instrument is where we got the whole thing of millimeters of mercury. So a standard unit of pressure being an atmosphere, because we have an atmosphere above us. For every 1 atmosphere, which is standard pressure, it pushes and creates a column that's actually 760 millimeters high, if it's mercury. Does anyone want to guess why we don't use water in these things? No. We could put it in a closed system so it wouldn't evaporate, but that's not a bad idea. Any other ideas? How is mercury so different than water? You can't drink it. Okay, well, because we're all going to run around and drink our barometer water. What? It's an element? No. Cohesion's not a bad idea, but no, there's something really specific. If I had a mill of mercury and a mill of water, there'd be something very different about those mills. Density. Very, very, very dense. So if we were to build a barometer out of water, it would be incredibly high. And Miss Masage and I actually made an attempt a few years back. It didn't work because we kept getting air bubbles. But the height was from this window down to the ground. And that wasn't, it wasn't 760 millimeters, I'll tell you that. And that's because the pressure of an atmosphere down on something that's this dense is going to make that height a little more usable. I nerded out 2 summers ago. I was at some university in Oklahoma. I don't remember which one. But there was a bucket at the base of this building and a tube going all the way up. And I was walking by with a bunch of English teachers, English AP teachers, and they were like, "What's that bucket?" I was like, "Oh, my God, it's a water barometer." And everyone thought I was really weird. But I knew what it was, and they didn't. So anyway, we don't use water in our barometers. You need to know conversions for units. If our standard pressure is 1 atm in millimeters of mercury, we already said it's 760. 760 is another pressure unit. Who remembers? Torr. Good. And then I heard Mr. Austin say it. Kilopascals. In physics, you use that during your pressure unit. You're going to be using kilopascals or kPa more so than atmospheres. Okay? But we like atmospheres. We have a better atmosphere in chemistry. Ha, 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 ha. You can tell them that in physics. That's why we use atmospheres, because we have a better atmosphere than they do. All right. So let's move on to some of the gas laws that you might have learned back in Chem 1. You knew some names, the first one being Boyles Law, and depending upon your teacher, you might have heard the little stories that we always tell all our Westlake students. The first being Boyle, and I'm going to pick on, who can I pick on today? I think I'm going to pick on Mr. Andrew, because he was almost late to class. I figured out why Andrew's always, like, really near the bell. He has a lady, I like how Will says lady friend. Yes, he has a lady friend, and I saw today. Smacky face? Yes, he has a little lady friend, and I think she keeps him from the bell. So anyway, so Andrew's getting ready to go to prom with his lady friend. And he, yes, this is in the video for all time. He goes to prom with his lady friend, but when he's getting ready for prom, he realizes he has a boil on his face. So he's peeved, PV. He's peeved, he has a boil on his face. Boyles' Law is the relationship between pressure and volume. If we increase the pressure on a system, you can kind of look at my hands. What happens to volume? Volume decreases. So an increase in pressure, decrease in volume. What's that relationship? Inverse or indirectly related. If we were to have these equal to a constant, the relationship would be like this, okay? Because if we increase pressure, we'd have to decrease volume to maintain that constant. So a really easy way to remember all these relationships is that combined gas law you learned in Chem 1, PV over T equals PV over T. Peas and vegetables on top of the table, even though peas are vegetables, so I don't necessarily think it's the best way to remember it. But if you cover up temperature, put your hands on top of temperature, you can see PV equals PV, and that will give you the relationship, okay? The way we're actually going to do problems, though, is through the use of dimensional analysis. If you are a plug-and-chug person in Chem 1, they teach you all the formulas and they let them plug in. That's fine. I'm not going to stop you. I just would prefer you use dimensional analysis because you're questioning what happens and if your answer makes sense. When you plug and chug, you don't think about whether or not that answer could be the right one. So when we're doing this, I'm just going to kind of tally what information I'm given from my problem. So in this first one, it says a sample of SF6 occupies a container of variable volume. What does that mean, a container of variable volume? The volume can change. So give me an example of a container with variable volume. A balloon, plastic bag, things like that, right? So if we have SF6, it says it has a volume of 50 mils at 700, whoops, I want to put that that's a pressure of 755. Calculate the pressure which must be exerted to lower the volume to 25 mils. Notice we have a set of conditions before turning into a set of conditions after. So what we're going to do is do a simple ratio. These are all linear relationships, so we're just going to take and start a dimensional analysis with what we're looking for. We're looking for pressure, so I'm going to start with pressure. 755 millimeters of mercury. Start a dimensional analysis. This is really, really easy. Going from our start conditions to our final conditions, what happened to volume? It decreased. Okay, I know you say half, but we're going to let the math tell us that. Right now, I just want to know the relationship. So if our volume decreases, what had to happen to pressure? Pressure had to increase. So I'm going to multiply this pressure by a ratio that's going to make the pressure go up. So I can either multiply it by 50 over 25 or 25 over 50. Which one's going to make the pressure increase? 50 over 25. So those of you who said halved it, I mean you were sort of, kind of on the right track. So tell us what our pressure is. 1510. So we had to double the pressure to cut that volume in half. So 1510, and I'm sticking with 3 sig figs, and the unit I'm going to get is always going to be the unit that I start with. Because we are working in proportions, our units don't matter as long as what we put in the dimensional analysis is the same. We had mils here and mils here. Well, look what happens. That cancels. Okay? We'll talk about temperature in a minute. That's going to be an exception to all that. Okay, let's move on to the next problem. Avogadro's Law, I don't have a story for because it pretty much just is a very common sense kind of a law. What was Avogadro responsible for? What did he come up with? The what? Yeah, what's that number? I know the number. What does the number stand for? What is it called? How about the mole? He came up with the mole. The mole. Okay, so y'all make things so complex. 6.02 times 10 to the 23rd. It's a mole. All right, so he came up with the mole, and the relationship that we're looking at in Avogadro's Law is that between volume and N stands for number of moles, and you get to PV equals nRT, perv nert, naked perv, whatever. The N stands for moles. All right? Well, that's a physics one. We don't do naked perv in chemistry. Again, better atmosphere. We don't talk about naked pervs in chemistry. So, looking at this, it's a common sense thing. If we have more moles, what happens to the volume? It increases. We have more volume, all right? And vice versa. So, what type of relationship is this one? This is a direct. As this one increases, that one has to increase if we're going to set that equal to a constant. So to solve a problem like this, this is showing us the conversion of oxygen to ozone. And they say, okay, suppose we have 12.2 liters of a sample of oxygen, and that sample contains 0.05 moles of O2. The question is, what would be the volume of the ozone if this reaction were to happen? Well, to figure out the volume of the ozone, we would need to know moles of the ozone, right? Can we figure that out? What's that silly thing we've been doing all year called? Stoichiometry. We're going to mole bridge from our moles of oxygen to moles of ozone to figure that out. And once I do that, I get 0.5 moles of O2 for every 2 moles of O3. I have 3 moles of O2. So how much O2 do I have? Quickly, calculators. 0.333. All right, so we have 0.333 moles. What are we going to do with those moles? We're going to put them in the same type of ratio setup we had earlier. We start with what we're looking for. What are we looking for again? Volume. So we're going to start with 12.2 liters. What happened to moles? Decreased. If moles decrease, what has to happen to volume? Volume decreases. So I'm going to multiply by a fraction of those two numbers. That's going to make that 12.2 decrease. What goes on top of what? 333 over 0.5. So my final answer to 2 sig figs is how many liters? 8.1 liters. Okay. Now we're going to look at our gas laws that are involved in temperature. Temperature is a little bit crucial to pay attention to because it's the one thing that I care about the units. Our units have to be in what? Who remembers? Kelvin. Why Kelvin? Who? Huh? Why? Well, there's no zero, but more importantly, there's no negative numbers. So the negative numbers in all our mathematical applications of gas laws would be a mess. So we need to be on a positive degree scale. I can outright tell you, you will not do a problem in this chapter using a straight up degrees Celsius. If you do, you're doing something wrong. When we get to thermo, we have a little bit of play as to when we can and cannot use Celsius, depending if it's a delta T and things like that. But in this unit, everything has to be converted to Kelvin. So say they ask for an answer in degrees Celsius. They give you your givens in degrees Celsius. Do you just use degrees Celsius? No. You take your degrees Celsius, you convert them to Kelvin, and then you convert them back to degrees Celsius. You have to utilize those numbers in the math. The two laws that do utilize good old temperature are Charles's Law and Gay-Lussac's Law. So I just wrote the combined gas law there for us to look at. Let's tell our little story here. Anyone first period had, some of them heard of Charles in Charge? Anybody know that show? Scott Baio, teenage heartthrob back in my day? No? Charlie's Angels, Charlie Brown. Where can you find all of those? On TV. So Charles' Law is the relationship between temperature and volume. As temperature increases, the molecules, what happens to them? They get excited, they move around, and what happens? Okay, everyone says they expand. What does that mean? You're telling me a molecule will get larger? They take up more space. You're saying if I take water, a water molecule that's this big, and I heat it up, it comes this big? No. So what would be a word for changing the spacing? They spread out, right? I don't want you to say they expand because it really makes me think you think they themselves get bigger. They don't. They just spread out, all right? So as temperature increases, volume increases. That's a direct relationship, and that's Charles's Law. If you look at the combined gas law, you can see the relationship here by taking out pressure, and you can see that this is direct. As that one increases, that one has to increase. Now, it's Gay-Lussac. It's not Gay-Lussac, but for the whole point of telling my funny story, I'm going to call it Gay-Lussac's Law. And so Alyssa and Lauren are in the mall, and they're shopping. They went to Forever 21. Alyssa found these really cute little, like, Madonna gloves, and Lauren found some of those funny glasses. They're going to go to an 80s costume party, and they're really excited. And they were walking, and all of a sudden Alyssa sees this guy. She's like, oh, my God, Lauren, he is so cute. And Lauren's like, just so you know, he's gay. I can't believe you didn't know he was gay. And Alyssa's like, oh, what a pity. PT. Pressure, temperature. It's a pity he's gay. Okay, so Gay-Lussac's is the relationship between pressure and temperature. As pressure increases, the molecules move faster. We could also reverse it and say as we increase the temperature, the molecules will move faster. They start to hit each other and the sides of the container more often, so that's an increase in pressure. So looking at this, if we get rid of volume, same thing, direct relationship between pressure and temperature. Here's our little conversion from Celsius to Kelvin. Must know, must do all the time. So let's do a couple problems here. A 545 mil sample of nitrogen gas, 545 mils, initially at, negative 220 degrees Celsius, is heated to 100 degrees Celsius. Calculate the new volume. All right, first thing you want to do is what? Convert, exactly. So I can do this math, 273 plus 100. What's this? Negative 20 plus 273? 53 Kelvin. All right, so now we can do our math. We are looking for volume, so we start with volume. 545 mils. What law is this right now we're looking at? Volume and temperature? TV, Charles's Law. All right, so as we're going from the beginning conditions to the end conditions, temperature increased. As temperature increased, what's supposed to happen to volume? Increase. So if the volume increases, we're going to multiply by a ratio of 373 over 53. The Kelvin cancel, leaving me with a unit of mils to 3 sig figs. I'm just going to say these are 3, all of these numbers in the problem. 3,840 milliliters. All right, the next one. Calculate the volume of a sample of helium at negative 33.0 degrees Celsius And 1.23 ATM, if it occupies a volume of 2.34 liters at 54.5 degrees Celsius, oh man, 1026, we got a lot of stuff to clean up in this problem. One thing is obvious, and that's the temperature we have to fix. What else? Well, let's just do that first. Negative 33 to Kelvin is 240. And then 54.5, 327.5 Kelvin. I have another big problem. Can I use this ratio like this? No, I have to be in the same unit. Which unit do you go to? At the end of the day, I really don't care. But I'll tell you now that when you're doing the ideal gas law, PV equal nRT, pervnert, that 0.08 Alyssa was talking about has units of liter atmosphere mole Kelvin. So those atmospheres are going to be commonly what we need to convert to. So just get into practice of converting to atmospheres. And to do that, for every 1 ATM, how many millimeters of mercury do I have? 760. So you're going to get quick at converting. You're going to know, like, divide millimeters of mercury by 760 to get to ATM. And what do we get? 1.25 or 35? 1.35. All right, so now we have everything we need. And we can start with what we're looking for, but notice, you have to be really careful in these problems. We're starting with our known on this side. These are the conditions that are coupled together. So we're going from this way to figure out that volume. So start with what we're looking for. We're going to start with volume. All right. Now, we have two different conditions changing this time, which you might think, oh, these problems are going to be so hard. No, you just do one at a time. And you totally ignore the other one because they're independently affecting your volume. So what do you want to do first, pressure or temperature? Temperature. So going from here to here, what happened to temperature? Temperature decreased. Temperature decreases, what happens to volume? It decreases, so I'm going to multiply by a ratio of 240 over 327.5. So my Kelvin cancel. Now I'm done with temperature. Forget about it. Now I'm looking at pressure. Pressure, though, decreased. When I decrease pressure, what happens to volume? Volume increases. So I'm going to multiply by 1.35 over 1.23. And it's doing the opposite thing. So they're kind of competing. Temperature and pressure are kind of competing against that volume. So what would my 3 sig answer be? Who won? Yeah, temperature won, right? Temperature actually got the whole thing to decrease. So if you are a fan of the equations, you could have solved this entire problem using the combined gas law. Peas and vegetables on the table. Peas and vegetables on the table where this is condition 1 and these are conditions 2. You could have plugged and solved that way. Again, do what you want. I prefer you to think through the problem because I kind of like students to think. I know, call me crazy. I'm so crazy. All right, last thing of the day is Dalton's Law. Dalton's Law is just more of an annoyance than a difficulty. It's not hard. It's common sense. In a nutshell, Dalton's Law says the total pressure of a system is equal to the sum of all the gases in that system. So if I ask for the pressure in this room, total pressure, we would say that that pressure is equal to the partial pressure of what gases are in here right now? Oxygen, CO2, what else? Nitrogen. Maybe some of you had some beans for lunch. That would be methane. That's a joke. All right. So anyway, the total pressure in this room is equal to the sum. So that is what Dalton's Law says. Where we apply it in these problems is because in order to collect gas, we often have to collect it over water in experiments. Collecting over water causes a bit of an issue. All of you in pre-AP last year collected gas over water, I know for a fact. You remember a little tube. You had magnesium and HCl attached to a tube, and you put your hands underwater, and you were collecting in a little baby test tube. And you put your thumb over it once all the water was displaced. You pulled the test tube out, and then you took a splint, right? And you tried to make it pop. What you were doing was collecting over water. When you collected over water, in your little test tube, yeah, you had your hydrogen that you collected, but because you collected over water, you also had some vapor, some water vapor. So your gas wasn't pure hydrogen. There was water vapor in there. When we're working on gas law problems, we need our samples to be pure and dry. So we have to get rid of the water from our pressure because these molecules are adding additional pressure to the container. So the total pressure of the container in the case of last year at pre-AP was equal to the pressure of the hydrogen plus the partial pressure of the water vapor gas. So looking at this problem, instead of hydrogen, they were collecting oxygen. It says when a sample of oxygen produced from a chemical reaction is collected over water, when you see that, you need to get sick in your stomach and go, oh, I have to do that whole subtraction thing. Every time you see collected over water. When you read it in a problem, underline it because you got to do that. The total pressure was 765 millimeters of mercury. Calculate the pressure due to only oxygen. Well, again, what was our total pressure equal to? It's the partial pressure of the O2 plus what? Partial pressure of the water. So we need to find this. So for somehow we need to get that pressure of the water vapor. At the back of your in-class problems, you can flip to the back page. You've got a list of water vapor pressures at different temperatures. Everyone find the water vapor pressure at 24. What is it? 22. And that's a coincidence. Has nothing to do with standard, okay? 22.4, but what's the unit on that? It's torr, which we're lucky because that's going to be the same as millimeters of mercury, right? Phew, so luckily our life wasn't that hard. So how would I go ahead and find the pressure of just the oxygen? Subtract, and what do we get for our oxygen pressure? $743. We didn't use a 24 in that was just to find it on the chart, so 3 sig figs. 743 millimeters of mercury, okay? So let's put this in an actual problem. This is the granddaddy of all these kinds of problems. If you can handle this one, you're good with combined gas law. You know totally how to do it. So let's just write down all this information. A 235 mil sample of gas, so that's our volume, was collected over water at a temperature of 28 degrees Celsius on a low pressure day of 738 torr. Report the volume it would have at dry, so that's another thing saying, hey, we got to get rid of the water. STP conditions. So what was STP? Standard temperature and pressure. What is STP? What's standard temperature for gases? 0 degrees Celsius or 273. This is going to be the only place we have a different temperature than room temperature. In thermochemistry and equilibrium, in electrochemistry, our standard temperature is actually room temperature. Here, we're at 0 degrees Celsius instead of 25 degrees Celsius because just by the nature of gases, because they're so light, if we're working at lower temperatures, our sample sizes would be more dense, the numbers would be more usable. So we're going to go ahead and work at lower temperatures for standard. And what would our standard pressure be in torr? 760. So I have to go from here to here, but I see a bunch of stuff wrong. So what do we have to do first? Convert this degrees Celsius to Kelvin. Well, I know 25 is 298, so that's 3 more. That's going to be 301 Kelvin. So I've got my Kelvin temperatures. Good. Now the problem is with my vapor pressure. I have a vapor pressure that's going to be less than the 738, because what is this vapor pressure really equal to? I mean, not vapor pressure, dang it, the total pressure really equal to the sum of the pressure of the water vapor plus the pressure of, we don't know, they didn't give us the name of the gas, did they? Nope. We'll just call it G for gas. So we need this in order to utilize, we need the dry gas in order to do the math. So look on your table and find the vapor pressure for water at 28 degrees and tell me what it is. 23? 28.3 torr. We know this is torr. So what is the pressure of just our gas? Just don't round yet. 709.7 torr. We'll round at the end. Okay. All right. Now we can actually start the stupid problem. That's how long it took us to set that up. Again, not a difficult thing to do. And now I lost. I can't get my thing back down. That's okay. I've lost my sidebar, unless it's over here. Here it is. So looking at this, we are solving for volume. So we're going to start with volume. 235 mils. Which condition do you want to deal with first, temperature or pressure? Temperature. So what's happening to temperature? It's decreasing. As temperature decreases, what happens to volume? Decreases. So we're going to put 273 over 301. Now let's look at the new pressure to the next pressure there. Pressure increase. As pressure increases, what happens to volume? Volume decreases. So another decrease, and it's going to be what over what? Over 760. And this is torr. So these go and those go, leaving us with mils. And to 3 sig figs, what are my mils? 199 mils. Okay? So again, this was the most perplexing. So I think the hardest part, and I don't even think it's hard, is just remembering your relationships. Think about your real life. If you had have you all had basketballs or footballs outside in the winter and you go out, and what happens to the balls? They get all deflated, and that's because the air inside, it didn't leak out, it's just cold, and so the volume decreased. All right, causing a decrease in pressure. You can think about collapsing. All sorts of real-life scenarios will make those relationships clear. So you have time to start your homework. I am donezo.